So I think we can get started today. And so the first topic is going to be recalling some basic facts about Newtonian gravity. Right? So the theory that Newton wrote down is based on a force, right? So a force which is minus g times one mass and the second mass divided by r squared times some unit vector. Right? And so in that force we have Newton's constant, right? And Newton's constant by now is fairly well known. It was already known quite well in the 17th century due to Cavendish's measurements. But in the units we use today, this is 6.67 times 10 to the minus 8 dyne centimeter squared divided by gram squared. But it is actually quite convenient for a number of things that we're going to discuss throughout this class to formulate it in what are so-called particle physics units. That is to write it in terms of h bar c divided by c cubed. That is, in other words, we can use Planck's constant and the speed of light to get out of g something that has the units of a length, right? And so this is called the Planck length. And so this is the Planck length squared. And this length, so, is equal to 1.61624 with an uncertainty of about 12 in the last digit, and then times 10 to the minus 33 centimeters, and then the whole thing squared, right? So in Newton's theory, there is this constant that appears that has a natural dimensions of a length squared in these units, right? And so these units can be, we can choose Planck's constant to be 1. We can choose the speed of light to be 1 by measuring distances and times with the same units. And then we have that this is just g is a length squared, the Planck length squared. So what is interesting, of course, is that what appears is an extremely small length scale. What is also interesting is that it is a length scale squared. Right? So it doesn't necessarily mean that there is actually a fundamental length, because it could be a product of two different length scales, to which we'll come back in a little bit. Right? So now from this we can introduce a gravitational potential. Right? That is, in other words, we write as F, the force, is equal to minus m times the gradient of a potential, right? And that is useful for a number of reasons that we already actually appreciate this aspect when we do electromagnetism, that it can be very convenient to have a potential instead of a force field. So as a result of that, we, for example, can write the potential for a point source as phi of x is equal to minus mg divided by x minus x naught, right? So we can write down the potential for a point source in this form, and then from that calculate the gravitational force. In general, if we have a mass distribution, then for a mass distribution we have that phi of x, right, is equal to some integral in d3x prime, right, of g times rho of x prime, some mass distribution rho of x prime divided by x minus x prime, just like we do later on in electromagnetism with a minus sign in front, because this potential is attractive. So that means that we can actually introduce a gravitational field. Right? We introduce a gravitational field denoted by capital G, which is essentially just the gradient of phi, right? So is equal to minus the gradient of phi. And this gravitational field then satisfies divergence of G is equal to minus 4 pi of G times rho of x. Right? So its source is the mass distribution, and this is essentially Gauss's law. Right? And from that we can write down Poisson's equation, which says that the Laplacian of phi is equal to 4 pi g times rho. 4 pi times Newton's constant times rho. And so that's Poisson's equation. Which is the analogous equation to what we do in electromagnetism when we discuss electrostatics. We have Poisson's equation as one of the fundamental equations of electrostatics. Fundamental because it applies to just about any charge distribution, right? So you give me a charge distribution that depends on x, right? And I will then, from that, compute the field as a function of x, and then I can infer what the force is. Well, that just about summarizes all the fundamental equations of Newtonian gravity. Basically done. We can write it in 1 or 2 blackboards, right? And that's all there is to it. I mean, those equations have very important and fundamental consequences, which have to do with the motion of the planets and so forth, the pendulum, and the system of n bodies as they interact with each other. Nevertheless, the fundamental equations are very simple. Right? I mean, comparatively, right? Compared to what we're going to see later on. And it's all formulated in terms of a single potential, phi, and a gravitational coupling. It will turn out, of course, that in general relativity, gravitational coupling is still the same. Right? So that's going to carry over the g. But instead of having one equation for a single scalar field, we'll have 10 equations, because that's how many fields there are in the general theory, right? We have the components of the metric, which is a symmetric tensor in 4 dimensions, which has 10 independent components, at least to start with. It will turn out that later on there's actually a few more. There's actually a few constraints, so there's less independent components of the gravitational fields. So a few more facts about gravity. Right. So gravity is special, right? It's special in a number of ways, and it was recognized it was already special back in the 18th and 19th century, right? And well, it's special because, number one, it is the oldest force. It is the oldest force. It's the one that was discovered first, right? And so it couples to everything. It couples to everything. If something has a mass or has energy, then gravity will couple to it. If it doesn't have a mass and doesn't have energy, then it doesn't exist. Right? So gravity couples to everything, which of course distinguishes it from electromagnetism, the weak force, and the strong force, because each of the other forces I mentioned couple to some sort of charge, which is characteristic of that. Gravity couples to everything. Right? So another thing that is, of course, fundamental to gravity is that gravity cannot be screened. Gravity cannot be screened. So there is another fundamental difference with electromagnetism. In gravity, there is no notion of opposite charges. Right? There's only one sign for the charge, which is attraction. And that attraction acts universally on anything that has energy or mass. Right? And so, well, there's another fundamental fact about gravity is that it is long range. It is a long-range force, right? It extends over very large distances, right? Much larger distances than anything else that we have, right? And except electromagnetism, but most of the time we're talking electromagnetism about bodies which are charge neutral, and then in that case, of course, the force falls off more quickly than 1/r. So you only have 1/r in electromagnetism if you have a point charge at the origin, which is not screened. So here it is long range, always, right? Even when we're talking about scales of the planets. And in modern language, right, that means when the range is infinite, it means that the mass of the gravitational particle is 0. Right? So gravity is mediated by a particle that has 0 mass. And that is the only way to explain the fact that it has really long range. Right? Really long range on planetary scales, but in fact it goes way beyond that. Right? It has a long range on galactic scales. Right? The motion of galaxies is interpreted in terms of potential. It goes like 1/r, which is therefore due to the exchange of a massless particle, if we believe in quantum mechanics, right? And finally, there is one more fact, right? 5. It is the weakest force. It is the weakest force, right? So, well, why is it weak? Of course, in the case of electromagnetism, we can state that electromagnetism is weak in a fairly unambiguous way, because we know that in electromagnetism, the fine structure constant, which is E squared over h bar c, is 1/137, right? Which is a small number, which is the reason why perturbation theory works well for electromagnetism, because there is a fundamental dimensionless coupling that characterizes the interaction strength. And that also goes for the other two forces, the weak and the strong force. They also have a dimensionless coupling constant, which in that case is not particularly small. It's small for the weak one, but not small for the strong one. Here, of course, the situation is a little bit more clouded by the fact that we have a coupling that has dimensions. Right? So you cannot really say that G is small, because it's this Planck length squared, right? But nevertheless, on the scales that we do laboratory experiments, because of this nature of the dimensionful nature of the G, the gravitational force is quite small compared to the other forces. And it's certainly true also at the level of atoms, right? Because if you go down to atoms, the gravitational force is completely negligible by many, many orders of magnitude compared to the Coulomb force, right? So there are these fundamental characteristics of gravity, which we have to keep in the back of our mind. And I think I would say that most of them already appear at the Newtonian level, right? The relativistic theory or even a quantum theory will of course, inherit this kind of properties, but they're already there at the Newtonian level, right? So we're going to get started in just a second, talking about the relativistic theory and how Einstein came about formulating a relativistic theory of gravity by considering the general relativity, right, the general transformations between frames. But before we do that, let me just trace a few steps, right? Steps in the development of Einstein's gravity, right? And so let me mention a few of those. I think you might be familiar, but nevertheless it is perhaps interesting to recall what a tortuous process this was for Einstein. That is, the first thing that he realized, and let's say around 1907, is that gravitational fields have a relative existence. Have a relative existence, that is, if you are given a gravitational field, say on Earth, it is possible to choose a frame where that gravitational field is removed. And that frame is associated with a freely falling body, right? A body that falls from the top of the Tower of Pisa. In that frame, there is no gravitational field. So in that frame, the laws that apply are the laws of special relativity. And so he realized in 1907 that you could do a coordinate transformation to remove the gravitational field. And of course, coordinate transformations are the kind of things that he had been talking about just 2 years before when he developed special relativity. Special relativity is all about coordinate changes, right? How the physics of two different observers is related by a Lorentz transformation. So here he realized that if you did something that was a little bit more the Lorentz transformation, you could remove the gravitational field entirely, and that was due essentially to the principle of equivalence between gravitational and inertial mass. That is, it would be true for all freely falling bodies that you would be able to remove the gravitational field by putting yourself into this frame where the body is falling. So there is a need to extend special relativity to frames which are not inertial, that it is not related to each other by just a Lorentz transformation, a Lorentz boost. And so to accelerating frames, right? So there is a need to take acceleration into account, the simplest, of course, case being a body that falls on the surface of the Earth. And yes?
Couldn't we already calculate accelerations in special relativity?
You could, but special relativity usually deals with two observers that are related to each other by a Lorentz boost, which is one is at rest and the other one is moving with respect to the first guy at a velocity v. And that v is constant, right? It is crucial that in the Lorentz transformation, the v that appears is a number, right? It does not depend on x. It does not depend on the location, right? So here we're dealing with, in fact, coordinate transformations between x and t and x prime and t prime, where somehow the velocity depends on x and we're allowing for acceleration. So that is clearly outside the framework of special relativity. So he had to think how to do it. And so he immediately, obviously from his background, realized the importance of more general coordinate transformations that would not fall under the rubric of just Lorentz transformation, which involve a constant v, right? So clearly this is something that he needs to look at. And the other third thing, right, is that if you look at the field equations for Newtonian gravity, right, and what are those field equations? Well, the one I just wrote down, which is Poisson's equation. Right, Laplacian of phi is equal to 4 pi rho. Well, Laplacian of phi is equal to 4 pi rho is not a relativistically invariant equation. So Newtonian equation for phi of x are not relativistically invariant. Right, so he realizes that the equations of Newtonian gravity are not relativistically invariant. Why they're not relativistically invariant? Well, they involve the Laplacian. That's chapter 1 of Jackson, right, where you have just the Laplacian. You know that, in fact, when you look at Maxwell's equations, there's more to it. And you end up eventually with an equation which is box phi equal to a source, right? And the box having also the d by dt squared term. So that's then relativistically invariant. So if you just have the Laplacian, that's not going to do it because the time doesn't appear, right? But the time has to appear if you have a Lorentz invariant formulation. So this is not relativistically invariant already at the special relativity level, right? Just at the basic special relativity level, we need a box. Right, we need a box somewhere, and that's not part of Newton's theory in any way, and so that has to come at some point. So these three considerations lead him to consider, first of all, the equivalence principle. The equivalence principle as a fundamental basis of his theory. Right? So the equivalence principle meaning the equivalence of gravitational and inertial mass being the statement that all bodies will fall with the same acceleration in the absence, of course, of friction and drag. So this fact that all bodies fall with the same acceleration and therefore you can go to that frame where they're all at rest, that is a fundamental ingredient in his theory, and it is in fact one of the pillars of general relativity, if not the pillar. So that's point number one. Point number two is that you will have gravitational redshifts. That is that if you have radiation, like electromagnetic fields or photons in a strong gravitational field, there will be effects due to interaction between gravity and the electromagnetic fields. And so he has a way to illustrate that, and that is through elevators. Right? Through elevators, he considers what happened when you have an elevator and you shoot a beam of light in that elevator. What is the difference between the elevator being at rest in a gravitational field or freely falling and so forth? And so he realizes that since a gravitational field is the same as having an accelerated frame, that what you would have and what you expect to have is some sort of bending of light. And well, he can imagine that such an effect is there, but he can't calculate it yet, because in order to calculate it, you have to have an equation, right, that does that. And so he realizes that there will be bending of light. Bending of light when you have a massive body. As the light goes past this massive body, there will be some bending. And so, for example, bending of light by the sun, right? You need a massive body because it's a small effect, right? And so the way for him to do this is to, instead of thinking of light as a wave described by Maxwell's equation, is to do things in a much simpler way, and he's of course very familiar with that, is to consider photons, which he invented, right? And for photons, you can treat them as particles where the relationship between the energy and momentum is the relationship that is appropriate for a massless particle. So he said, well, I think I can compute the bending of light by just thinking of them as particles that do have an energy, right? And as a result of their energy, they will be bent in the field of the sun. And so this is all 1907. Right? It's 2 years after writing down the theory of special relativity, he starts to understand what the ingredients of the new theory would be, right? And he also understands that something funny will happen to the geometry. And that the geometry will be curved, that there's going to be some effect of curvature. And the way for him to realize that is that he considers a table that is spinning, right, at some velocity, about an axis, right? So this is our axis right here. And he considers what happens to an object or an observer that sits on the periphery of this disk that is spinning. He imagines that this disk is spinning pretty fast, right? It is spinning so fast that the velocity at the periphery is comparable to the speed of light, right? So it's a very fast spinning disk. And he says, well, if the object at the periphery is spinning with a velocity which is comparable to the comparable to the speed of light, then we will have length contraction. That means that the periphery will look shorter than what it's supposed to be, and so it will actually look more like like this, right? There's going to be some curvature, right? And so that means that the relationship between the radius of the disk and the circumference of the disk is not what you would expect on the basis of flat space or Euclidean geometry, right? Because the periphery is kind of contracted, so it's squeezed down. Even though this distance, right, this distance here, which we can call r, is going to be the same, right? So this r is the same, right? But the circumference gets shorter because of length contraction. So he says, well, that can't happen in flat space, right? It can't happen. It has to be curved, right? So in 1907, he realizes that funny things will happen and that there is a possibility that we're not talking about flat space anymore. And so that perhaps one should consider non-Euclidean geometry. Right. right? Non-Euclidean geometry where space-time is curved. And so these are all kind of ideas that he has in his mind, but that he cannot quite formulate yet in terms of mathematical equations. He can see where he's going and what should come out of it, but it's all based on intuition and visualizing things as opposed to some sort of concrete mathematics. So in 1911, he starts to realize that the bending of light by the sun is observable. He starts to realize that the bending of light by the sun is observable. How does he do that? Well, he has some sort of order of magnitude estimate, right, which is based on the energy of a photon, right? He knows that. He knows what the energy of a photon is in the visible range coming from some faraway stars. He knows what the mass of the sun is, the diameter of the sun, so he can do an order of magnitude estimate, and he finds out that it is not a minute effect. It is large enough that through some rather accurate observations you should be able to see it. He actually calculates it, and the calculation is off by a factor of 2. So he actually ends up getting a number which turns out to be incorrect because it doesn't have the general theory. And again, he uses the relationship between energy and frequency that is appropriate for photons. So he uses his formula, E is equal to h nu, to determine how much this bending you expect. And so again, he needs an equation to calculate this bending of light accurately, going beyond just an estimate based on simple equations. And he has an equation in 1912 for the C field. So let's write out this equation because it's interesting. It will have nothing to do with what will come later. His equation for the C field is that the Laplacian of the C field is equal to some constant times the C field itself times some coupling sigma plus some other coupling 1/2 alpha times the gradient of C squared divided by, again, the C field itself. And that's his equation for the bending of light. And what is the C field? Well, you can imagine that the C field is related to C, which is the speed of light. So he has now a theory, a candidate, where the speed of light is in fact not constant, right? But C depends on x, right? C is a function of the position. And he has some sort of nonlinear equation that tells us how this speed of light depends on the point x and therefore is modified, for example, by the presence of the sun. And it is still a scalar equation. So in 1912, he still has only one component for the gravitational field, which is the scalar, which instead of being phi is called the C field. And so he's still far away from understanding that actually the theory in the end will look completely different, that there's going to be something else, not the C field, but the metric. Right? So he's kind of wandering off into the wrong direction. He ends up with an equation which is quite ugly, and he thinks, though, that it might contain some of the seeds of the correct theory, and it does indeed have the bending of light as one of its effects. And at about the same time, in 1912, in fact, in August 1912, there is a start of the Marcel-Grossmann collaboration. So who was Marcel Grossmann? Well, Marcel Grossmann was one of his friends from when he was a student, except Marcel Grossmann was a mathematics student. So he studied mathematics, and part of mathematics at that time was to learn a little bit about the theory of surfaces, which meant differential geometry and maybe a little bit also of Riemannian differential geometry, which is differential geometry applied to manifolds which have dimension greater than 2, right? And so he had done a little bit of that, and he had learned that when you encounter differential geometry, there's lots of indices. And so now you have to deal with all these indices, and you raise them and you lower them. And he tells Einstein, look, there is a fundamental object in that differential geometry business. It's called the G mu nu. What's the G mu nu? Well, the G mu nu is a thing called metric. And if you have this metric, then you can calculate the affine connection, which is something we'll see later on in this class very soon. And from that, you get the curvature. And you have this thing called the Riemann tensor, and that tells you the curvature. And so Einstein and Grossman sat down and learned all these things. Grossman had to remind himself what it was about, and Einstein had to learn it from scratch, because in 1912, he was still playing around with the single scalar. And so Grossman tells him, look, there is a G mu nu of x. And from that, you can calculate what is called the affine connection, gamma lambda mu nu of x. And from that, you can calculate the Riemann tensor, all its contractions, which are these things. And that is what we need to learn. That is what we need to learn, because that's the right way of describing what you, with your intuition, recognized as one of the key ingredients of the general theory of relativity, that is curved spacetime. Curved spacetime is described in terms of these objects. And so out of this Einstein-Grossman collaboration came a number of papers which finally introduced this new formalism, right? And one of the fundamental realizations at that time is that, first of all, there's 10 fields, of course, and not one. So this is really way off, this theory here, right? Because it deals with a single scalar field. And the other thing is that this G mu nu is now related to the Newtonian potential. And they find that it's the G naught naught, which is minus 1 plus 2 phi of x, right? That it's the naught naught component that what appears in the Newtonian theory. So the Newtonian theory contains, in fact, one piece of that metric, but it's just the naught naught component. And then there's more which are entirely new, right? Which is, of course, not very different from electromagnetism, where in electromagnetism, once you've gone through a few chapters of Jackson or whatever your favorite book is on electromagnetism, you realize that the Coulomb potential phi is part of a bigger field, which is the E and B fields, or if you want, phi and the vector potential, right? It's only just a component of the whole 4-vector business. And so after, of course, they realized that this was an essential step, it became fairly easy to write down a set of equations that would describe relativistic gravity. So now we go back to 1907. And we start with the equivalence principle. So we talk about the principle of equivalence. Which is the foundation, right? One of the foundations of GR. And foundation of GR is this principle of equivalence. And so the idea is that, right, so the statement of the principle is that if you have a particle in a gravitational field, and that particle could be just on Earth, right, on the Tower of Pisa, for example, then you have that the acceleration is equal to g, right, the acceleration on the surface of the Earth. But the coefficients that come in on the two sides are somewhat different, right? We usually write it in this way. But in fact, we have, on the one hand, the inertial mass times the acceleration. So that's, if you want, the right-hand side of F equal ma. And on this side, we have the gravitational mass. So we have the inertial mass and we have the gravitational mass. Gravitational mass, right? So the statement is that those two masses are identical. Right? They're identical. So that means that the acceleration, right, the acceleration is equal to mg over mi times g, where this ratio here is unity. And this ratio here is unity. So that is the fundamental basis, right, for the general theory of relativity. And this was verified in a number of experiments, starting with Cavendish and later on with Eötvös. Where you can in fact test whether this is true, whether it is true that in fact all bodies fall exactly with the same acceleration, and that there is no dependence of this these constant mi and mg, for example, on the composition, right? You might think that the ratio would be somewhat different from wood as opposed to iron, as opposed to lead, and so forth, right? And so nowadays, actually, there are analogs of the original Eötvös experiment, which was done early in the 20th century, which established this equivalence to about 1 part in 10 to the 12. Right? It was 10 to the 11 a few years ago, and now it's down to a part in 10 to the 12. So this is one of the most thoroughly tested relationships, right, in physics, because when we can actually establish that something is true to 1 part in 10 to the 12, that's a pretty good statement. And so this equivalence of gravitational and inertial mass, right, the inertial mass representing a resistance to acceleration, right? You try to accelerate this body and it resists. That's the inertial mass. The gravitational mass is kind of a gravitational charge, right? It tells you how much a certain body is attracted by a gravitational field. So they're kind of fundamentally different at first, but they happen to be identical, right? And of course, we wonder why that is exactly the case, right? But it is a statement that this seems to be true, right? Not in absolute terms, but at least to 1 part in 10 to the 12, and that those two quantities are equivalent. So that, of course, has as an important consequence the fact that we can cancel a gravitational field by a change of coordinates. So let's see how that comes about. Right, so we consider a body that is falling in a gravitational field. It will be simplest to just consider one, again, on the surface of the Earth. All right, so example. Right, so we have, of course, at first we're going to discuss things that are non-relativistic, right? So we forget a little bit of what we've done in the last few lectures. And so we just consider a particle that follows Newton's law. So the second derivative of the coordinate with respect to the time is equal to the acceleration due to gravity. So is equal to m times g, right? And there could be other forces as well, which are non-gravitational, and therefore that we will at this stage ignore, right? And so now the point is that we can remove this force. Remove this force by doing a transformation which is, well, it's not a Lorentz transformation, and therefore in the non-relativistic case that would be a Galilean transformation. So it is non-Galilean transformation, which reads as follows, that x prime is equal to x minus 1/2 gt squared, and t prime is equal to t. So with we do this transformation, and this transformation is, because of the appearance of g, is the same for all bodies, right? Remember, the universality, right, of gravitational attraction means that they all fall with the same acceleration, which means that we can remove the effect of gravity by a single transformation for all these bodies that are in a gravitational field. And doing this transformation just eliminates the gravitational field. So G gravitational field, G, is canceled, right? And as a result of that, we get a new equation, right, which is m times the second derivative of x prime squared with respect to t squared is equal to 0. Right? So this simple example, this single transformation, shows that if you have, right, so here is your tower, right? So if you have a body that falls down here, right, in a gravitational field, and if the original frame is this x and t frame, right, and that would be the lab frame, so you're looking at this object falling down from the Tower of Pisa, then you can do a transformation to a different frame, and that different frame is the freely falling one, right? So that's the frame that is freely falling and has a t prime and an x prime. And in that freely falling frame, if indeed there is this equivalence between gravitational and inertial mass, then in that freely falling frame, there are no forces. There are no forces. So the body is just are basically subject to the law of inertial frames, like we did in special relativity. So statement of the principle of equivalence, right? So we want to state it now in a way that is more general than the simple case which is described here. We want to phrase it in a way that will have universal applicability, right? And that will be therefore something useful for developing the general theory. And so the general statement is that, and let me just say it in words instead of trying to write it out, and that is that at every space-time point, right, so you pick a space-time point which has coordinate x and t. So at every space-time point, we can do what? Well, we can do a transformation, and so that general space-time points is going to be subject to a gravitational field. Right? Otherwise, it's not very interesting. So at that space-time point, it is possible to choose a locally inertial frame. It is possible to choose a locally inertial frame, which is a frame where the effects of gravity are removed. So where gravity is canceled, which means that in the region around that point, we are dealing with an unaccelerated Cartesian frame. We are dealing with an unaccelerated Cartesian frame. Right? So the picture we have, let me draw it out on this side, is that we have a point in space-time, right, x and t, and that point will be in some gravitational field, right? And there is a region of space-time around this point where we can choose a coordinate system which is Cartesian, right? Cartesian means that it follows the laws of special relativity, essentially, right? It is written in terms of orthogonal coordinate system. So these are the coordinate systems of special relativity. So that means that in this region, I can choose an inertial frame. I can choose an inertial frame. So generally what you do have is a gravitational field that varies over space and time, right? So the gravitational field will have one value here, it will have one value at some other location, right? But if you're looking at a sufficiently small region, that gravitational field around that relatively small, in that small region around that point, is going to be fairly constant, right? It will not vary by a whole lot. And in that region, we can make the transformation that is just discussed here, where you change from one coordinate system to another one, which is freely falling. And in that freely falling coordinate system, the laws are the laws of special relativity, because you have removed the effect of a gravitational field. You have equations of motion that are just the ones for a space where you don't have any sort of effects of gravitation. So that means that in general, if the gravitational field is varying, you have to use regions which are sufficiently small so that this applies, right? So in general, you have wide variations of g over some scale, right? So g of x, or whatever describes gravity, is varying over some scale. And so this region here has to be small in some sense, right? And so being small means that the region has to be small enough that derivatives of the g are fairly negligible, right? And so that is the statement of the principal equivalence. So let me say it one more time, right? The statement of the principle of equivalence is that in an arbitrary gravitational field, it is possible to choose locally a reference frame at a point such that in that frame, the laws of special relativity apply. And therefore, the gravitational field has been removed, right? And those frames are inertial frames, or if you want, you can call them also freely falling frames. Right? Inertial frames are the same as freely falling frames. So at every point in a gravitational field, it is possible to choose this coordinate system, which is attached to whatever body is falling, right? And in that coordinate system, which is freely falling, there is no effect of gravitation anymore, right? So you can visualize that as, again, a body falling from the Tower of Pisa or an elevator, right? Where the steel wire that holds the elevator has been broken, right? So it freely falls down, and all the objects fall with the same velocity, and the laws of special relativity, or even Galilean kind of environment where you have just Newton's law still applies in the absence of gravity, right? So that is the statement of the principle of equivalence in its most general form, which does not imply any particular setup like we have in the case of a gravitational field on Earth, where you have a little g, right? So this is more general. Yeah, somebody had a question. No. So now what do you do with this, right? So we need to turn this into some sort of useful expressions that will allow us to calculate something, right? Yes?
In this frame, should we use t prime?
T prime, but T prime and T are the same, right? T prime and T are the same. So if you want, you can put a T prime here. You're welcome to do that, but the two are the same, right? So now we want to, as I said, we want to be able to write down some equation that we can work with, right? This was what I just illustrated here was rather special, right? And so more general framework to what we had on this blackboard a second ago. And so in particular, how do we in general describe this issue of gravitational forces and how they can be removed by the choice of an inertial frame? So gravitational gravitational forces, right? So we are going to call this freely falling frame right here by coordinates which we denote by psi alpha, right? So we have some general gravitational field, and we state that at every point it is possible to choose coordinates which we denote by psi alpha, such that these coordinates are the ones that we would employ if we were to use just the laws of special relativity. So these are the so-called freely falling coordinates. Or inertial. Inertial coordinates, psi alphas. So what are the equations of motion for the psi alpha coordinates? Well, we have removed the gravitational field, and we stated that there's not going to be anything else besides the gravitational field. So if there's nothing left, then the equations of motion have to be that the acceleration psi alpha with respect to tau squared is equal to 0. Right? So in the freely falling coordinate system, the only equations we have in the absence of any sort of non-gravitational force is that there is no acceleration. There is no acceleration, right, in the freely falling frame. Right? So we're assuming that there are no other forces, which in view of what we discussed in the previous lectures means that this little f alpha is 0. Right? So that includes the effects of electromagnetism or any other sort of force that we can think of which is not gravitational. So now we're going to work ourselves back to the lab frame. Right? So we have this frame out here, which is described by coordinate x mu. So this is the lab frame. Right? And so what kind of lab frame? Well, it could be any lab you want. So it could be, stationary with the Earth, stationary with Jupiter, stationary whatever you choose to be stationary with. The only coordinate system that is really quite special in this context is the psi, because the psi is in fact attached to the body that is falling in a gravitational field. The psi is very special. The lab frame could be all sorts of different lab frames depending on how you look at these objects from the outside as it is freely falling. So the lab frame we denoted by x mu, right? And this x mu is going to be a function of the psi alpha, right? There is a transformation that leads from one to the other. We saw what the transformation looks like a second ago when we looked at a body that is falling from the Tower of Pisa, right? But that transformation could be more complicated and could in fact involve the time as well, right? So we want to write it in the most general form as a transformation from the original freely falling or inertial coordinate system psi to a new coordinate system x mu, which would be some sort of lab frame. All right, so as I said, we're going to work ourselves backwards, and so that means that we are going to rewrite this equation in terms of the lab frame coordinates. Right, so we have that the second derivative of psi alpha with respect to the proper time is equal to 0. So the second derivative of psi alpha with respect to the proper time, right, that's of course the appropriate equation to use, at least in special relativity, that we have this proper time, which is an invariant. So this thing is equal to 0. And now we're going to rewrite it in terms of, well, we first take out one derivative with respect to tau, and then we have the psi alpha with respect to tau. And so we're going to write that as d psi alpha with respect to x mu, right? And times dx mu with respect to tau, right? So that's how we brought in the coordinate, right? Remember, differentials can be handled just like they're fractions, except that here we have a sum over the index mu. right? And so now we carry out this second derivative, right? And the second derivative means that the first thing is we're going to take a derivative of x mu with respect to tau. In fact, it's enough to just write a derivative like this because it's a single parameter. So we can write this as d psi alpha by dx mu. Right, and then times the second derivative of x mu with respect to tau squared. So that's what we get when we act on this term here. Right? And then we have a second term, which is what happens when you act with d by d tau on this. When we act with d by d tau on this, we're going to write again the d by d tau as a derivative with respect to the x, and then dx by d tau. So we're going to write this as the second derivative of psi alpha with respect to the x mu and the x nu. Right? And then times the derivative of dx mu by d tau and dx nu by d tau. Right? Now, incidentally, I should mention that I think initially we're going to do some of these calculations in detail because we want to understand and see how this works when you do all these manipulations with changing variables and some repeated indices and contracting and so forth. Later on, as we progress in the course, we are not going to do all these things in excruciating detail because you will notice that after a while the kind of manipulations repeat themselves and they're always pretty much of the same type and style where you change from one variable to another and use this rule of writing derivatives. So anyhow, this is a kind of a rather very simple manipulation, and so we are going to now multiply this on both sides. We somehow would like to be able to get rid of this. Get rid of this, and so that is easily done by multiplying, if you want, by the inverse of that, right? And so we're going to multiply by dx lambda by d psi alpha. Right? So then we have this quantity times that, which is just a Kronecker delta. Right? So let me write this on top on this side so it's more readable. So we have that 0. 0 is equal to dx lambda by d psi alpha, right, times d psi alpha by dx mu, right? And then times the second derivative of x mu with respect to tau squared. Tau squared, right? And so this thing here, because alpha is summed over, right? So you can get rid of these differentials if you want. So you get just dx lambda by dx mu, and that is just delta lambda mu. Okay, so that is just a Kronecker delta, right? Which turns, of course, this index mu into an index lambda, right? And then we have the rest, right? And so the rest is, again, this factor of dx lambda by dx alpha times this piece here. So again, dx lambda by d psi alpha, right, times the second derivative of psi alpha with respect to x mu and x nu, because I think that's what I had out there, right? And then times the derivative of x mu with respect to tau and dx nu with respect to tau, right? And so this is equal to 0, right? And so what do we do with this? Well, not a whole lot at this point. We are just going to take this object and give it a name. Right? So we are going to call this gamma lambda mu nu. Gamma lambda mu nu. Right? We'll come back to it in a little bit. And so that means that we have an equation, right? Second derivative of x mu with respect to tau squared plus this quantity, gamma lambda mu nu, times dx mu by d tau dx nu by d tau is equal to 0. And so we have achieved what we wanted, to write out what the equations of motion are for a body that is initially freely falling in a gravitational field, right? So initially it was in this psi alpha frame, and then it is viewed from this other frame, which is the lab frame. Right? And so x lambda for the first term thing. So this is the equation of free fall. Equation of free fall, right? Or, well, for obvious reasons, because that's how we derived it, right? Or equation for the geodesic equation. Now, why it is called the geodesic equation is not obvious at this point, right? But it goes by those two names. It's either the equation of free fall, from what we discussed, that is clear, or the equation for geodesics, because it will turn out that particles in a gravitational field in this general theory follow geodesics in space-time, which are the shortest or perhaps the longest paths, right? And so this object here is called the affine connection. This object here is called the affine connection. And well, at this stage, of course, it is really ugly, this equation, right? I mean, irrespective of the fact that we have been able to call this entity by the name gamma, right? But nevertheless, it is quite ugly. Why it is ugly? Because this equation seems to depend on the coordinate system psi alpha, right? It is, the gamma is obtained by calculating certain derivatives of one coordinate with respect to another coordinate, right? And of course, the first coordinate is special, the psi. It's a very special set of coordinates which is attached to the freely falling body, and the x is general, right? So what we would like to be able to do is to somehow write down the equations in terms of something that does not involve psi. So it is desirable write equations in terms of x mu, this coordinate x mu, and perhaps other things as well, but being able to get rid of the psi alpha, right? Being able to eliminate a reference to this very special coordinate system, which is the one that is freely falling. And that, of course, has not happened yet at this stage, right? So we'll come to it in a moment. Now, let us look at the proper time interval, right? And the proper time interval, d tau squared, you will remember that this is equal, right, eta alpha beta dx alpha dx beta, right? You remember that that is how it was defined in special relativity. And why is it true that it applies here as well? Well, because, of course, in the freely falling frame, which is the psi one, the laws of special relativity apply, right? So in that frame, it is certainly legitimate to write it in this form, and this form is correct. But now what we can do is we can rewrite this as minus eta alpha beta times, we bring in the coordinates x mu. So write it as dx alpha, and we use partial derivatives, d by dx alpha dx mu, and d by, psi now, because that's what our coordinate system is here. So d psi alpha by dx mu and d psi beta by dx nu, and then times dx mu and dx nu. Right? So we can write it in this form by just changing coordinates. And now this object here, we're going to give it a name, and we're going to call it g mu nu, and in general it will be a function of x. It will be a function of x because we are looking at a specific point, right, in this manifold. So it's going to be g mu nu of x, and so this is equal to minus g mu nu times dx mu dx nu. Okay. And so this is definition of the g mu nu is this object here. And so this is called the metric at x. Right? So d tau squared is equal to this. Right? Well, we don't know the metric, right, until somebody tells us what the psi coordinates look like and what the lab coordinates look like, and then we can calculate the derivatives and we'll get an expression for dg mu nu. Nevertheless, the metric is something that we already encounter when we do, for example, spherical coordinates or cylindrical coordinate system. You have that the increment of the coordinate they can be translated into this d tau squared quantity, and the coefficients that come in are the metric already in those simple coordinate changes, and they're usually constant. So we now want to find a way to calculate this gamma lambda mu nu. So actually, let me go over to the other blackboard, because it's nice to have that equation sitting there. And so it would be nice to have this gamma lambda mu nu in terms of, say, the coordinate x mu, and not in terms of these inertial coordinates psi alpha, right? And so such a relationship exists. Such a relationship exists. And how do we obtain a relationship like that? Well, we start out from what I just erased, which is the g mu nu at x. So it's always at a point, which I'm not going to write, but that's always intended. The whole point here is that we do have coordinate transformations which vary from point to point. Right? Because we don't want to have anything like gravitational fields which are constant, right? So this g mu nu, remember, was equal to d psi alpha by dx mu and d psi beta by dx nu, right, times eta alpha beta. Right? That is how it was defined. And so now what we are going to do is take the derivative of this g mu nu with respect to the coordinate, and in order to do that we have to introduce one more index, right, because we don't want to mess up the two indices we already have, mu and nu, so we call the third index lambda, right? And so now we do, again, I'm going to do this in some detail because I think it's good to do that at the beginning, to do some of these index manipulations explicitly so we see how they work. And so we're going to use pretty much the same procedure we used a moment ago, where you can write the derivative with respect to x as the derivatives with respect to something else, right? And so we use the fact that the g mu nu is given by this expression, right? So that means that we have the second derivative of the psi alpha. So we now focus on the first term, right? Second derivative of the psi alpha with respect to x lambda, which is the new derivative, d by dx lambda, and then the old one, of course, which is d by dx mu, right? And then times the second term, which is the derivative of psi beta with respect to x nu, right? And then times the 8 alpha beta. And so that's the derivative of the first term, which is this one. And then we have the derivative of the second term as well. So plus d by d psi alpha by dx mu, which we just carry over, which is this first term, times the derivative with respect to x lambda of the second term, right? So plus the second derivative of psi beta now with respect to x lambda and x nu, right? So you got to keep track of all these indices, right? So we have the d by dx lambda here, d by dx lambda, and d by dx lambda here appearing as well. It's just the derivative of the product, times, of course, the eta alpha beta. Right? Eta alpha beta. Now the thing is that if you look up here, we do in fact have that these second derivatives, let me use a color pen now, the second derivative of the, right, if you focus on this object here, right, that's precisely what appears in the definition of the affine connection, because that's what we have here, right? Okay, so the only slight difference is the prefactor here in front, because the affine connection contains this factor as well. So that means that the second derivative is gamma times the inverse of this, right? This is just a matrix, so we multiply it by the inverse, right? So we can rewrite this. So let me write it down here, right? That the second derivative of psi alpha with respect to x lambda and x mu, right, is not going to be just the gamma, but is going to be equal to gamma. Now we also need to introduce one more index, because we can't use the indices we already have. So the new index is going to be a rho. So gamma rho mu nu. And then times, as I said, we want to isolate the second derivative. So it's going to be this gamma times the inverse of that, right? So times d psi alpha by dx rho. Okay, and so we're going to stick that in here, right, for that. And of course we have the same thing on this side, right? We have the same thing here as well, right? So we have this expression in two places, right? So we have that here as well. Okay, so very good. So we're going to do that over on this side. Over on this side. So we have that the second derivative of g mu nu with respect to x lambda, right, which is what we calculated here, is going to be equal to some gamma. So the gamma is the gamma rho, right, with lambda mu. And then two of these factors, dxi by dx, two of them. So dx psi alpha by dx rho, the first one, and dxi beta by dx nu. And then times this 8 alpha beta, which you just drag along. Now remember that there is no derivative with respect to of 8 alpha beta with respect to x lambda, because of course 8 alpha beta is just our minus 1, 1, 1, 1, right, and 0 everywhere else. So this is clearly a constant, right? It's a constant thing. So when you take the derivative with respect to x lambda, that's always 0, right? So that's why there's only 2 terms when you take this derivative and not 3, right? Right? So that's one term. Right, and then the second one is gamma rho lambda nu. Right? The structure is almost the same, right, because of the symmetry of the original expression. So the gamma times dx alpha by d rho, d psi alpha by dx mu, and then d psi beta by d rho. X rho, and then again times eta alpha beta, right? Well, that has simplified things a little bit, because now we recognize that this and that are equal to what we just defined a moment ago to be equal to our metric, right? So this is in fact equal to g rho nu, right? The two indices here, rho nu, alpha and beta are summed over, and so this is our g rho nu of x, right? Similarly, in this case, the alpha and beta are summed over, and we have the mu and rho, right? And so this is our G mu rho, right? Remember that by construction, the metric is symmetric, right? Obviously, G mu nu is equal to G nu mu. That's obvious from the definition, right? It is symmetric quantity. So we can always reorder the indices any way we want. And so that means that we have, in fact, obtained the following expression. We have obtained that the derivative of G mu nu with respect to dx lambda is equal to gamma rho lambda mu. And now what we have here is just a metric, G rho nu, plus gamma rho lambda nu times G rho mu. Right? Well, that is very nice. Why is it very nice? Because we have, in fact, been able to get rid altogether at this stage, seemingly, perhaps, of an explicitly appearing psi. Right? This does not contain psi at this stage. Right? The psi might very well be hidden in the gamma, but at this point there is no psi here. There is no psi alpha. Okay? Well, what that suggests is that we should be able to actually solve for gamma. Should be able to solve for gamma lambda mu nu, and that is indeed possible, right? It is possible by just taking suitable linear combinations, right? So what we are going to do is we are going to take dg mu nu by dx lambda, which is what we just had. Right? That's this one. And now what we can do is we can kind of permute around these indices, right? And so by trial and error, we have to find out what suitable combinations will work. And the suitable combination is G lambda nu with respect to x mu minus G mu lambda with respect to x nu. So we take this linear combination, and now we just read off each one of those three terms, right? We just read it off because we have the expression here. So we just substitute. And so it's one term plus a second term, which is almost the same, minus the third one with some slight permutation of the indices. And this happens to, right, when you work it out, I'll leave that to you as an exercise, that there's lots of cancellations, and the only thing that survives is G rho nu times gamma rho lambda mu. So we have been able now at this stage to have an expression for gamma in terms of derivatives of the G. Well, not quite, because we're still stuck with this G, okay? So how do we get rid of this? Well, this can be viewed as a matrix, right? The G can be viewed as a 4x4 matrix. So that means we're going to multiply by both sides by G to the minus 1, the inverse of this matrix here, and actually multiply also by a factor of 1/2, and then we have an expression for gamma, okay? So that means that we need to define inverse of G mu nu, and of course that depends on x, right? And the inverse of G mu nu, this was the great invention, if you want, of Levi-Civita and Ricci, is instead of writing it as G to the minus 1 and having this minus 1 appear everywhere, is to use indices that are raised to denote the inverse. Right? That seems at first rather strange, but in fact it works beautifully, and it really streamlines and simplifies the formalism. Now Einstein himself actually called G to the minus 1, he had a different name for it, he called it gamma. So at first Einstein did not use this Levi-Civita connection, so every time he had the inverse of a metric, he called it by another name, which was gamma. So we are going to use, though, this Levi-Civita convention, and as a result, we're going to define the inverse of G mu nu to be a quantity that has the indices raised, and so we're going to write it with the indices upstairs, G nu sigma times G rho nu. And when you take, so this is G minus 1, and this is the G. And when you multiply the G times the G minus 1, you should get the identity. And the identity, of course, is a 4x4 matrix whose entries along the diagonal are equal to 1. So that is our good old delta sigma rho. So we have to define, right? We have to define the inverse of the matrix, of the metric, right? And well, usually that inverse will exist. Usually the change of coordinate is non-singular, so that this matrix inverse exists. And well, if we do that, then we manage to get rid of this thing. And on this side, we're going to have g to the minus 1. And that g minus 1 is our inverse. So finally, the result is that gamma sigma lambda mu. We try to keep the indices as much as we had them here before without changing their name. So this is equal to 1/2. So the first entry we have is now this inverse, right? So it's going to have indices upstairs, g nu sigma, right? And then it will have 3 of those terms, which you can just copy from up there. So it's the derivative of g mu nu with respect to x lambda, is the derivative of g lambda nu with respect to x mu, lambda nu with respect to x mu, and then the third term is minus the derivative of g mu lambda with respect to x nu, and then close parenthesis. And so now we can check whether everything works. So we have 3 free indices, sigma, lambda, and mu. And on this side, we have indeed the sigma, which is upstairs, and the lambda and the mu, which is here, and then the sigma, which is the sigma is a free index, and the nu is summed over. So there is a nu here, and a nu there. So you can see that the index that is being summed over, sometimes it is convenient to use color. So the index that is summed over here is the nu index. So nu, the nu appears first in the second position, then it appears here as well, and then finally in the third term it appears here. So in fact, now this is not something that one easily remembers, and so perhaps there is a shorthand form which you can refer to, and I will refer to it a number of times without having to write down the indices explicitly. And so shorthand is that gamma is equal to 1/2 g to the minus 1 of the derivative of g plus some other derivative of g minus a third derivative of g, where the derivatives are taken with respect to, with different indices and things like that. And so that would be a shorthand for this, right? So we have been able, so what did we achieve? We did achieve something remarkable, because in the definition of gamma, this affine connection, which enters the equation of free fall, right, second derivative of x mu with respect to tau squared, we have been able, that affine connection, to write it entirely in terms of derivatives of the lab frame coordinates, right, which are not special. They could be anything. What was special was the freely falling frame, because that's a unique frame that is attached to the body that is falling, right? The lab frame could be anything, could be like this, could be like that, could be moving, could be accelerating, could be doing all sorts of things. It does have a g mu nu, right? It does have a g mu nu, and which tells us what the proper time intervals are. And if we know that, then we know everything, because we can calculate these derivatives, and we have this gamma, and we stick that into equation of free fall, and then presumably we can solve that. So that is a remarkable achievement, right, from at least from a mathematical point of view, that we have gotten rid of the psi alpha entirely, right? So the psi alpha is gone. Psi alpha, there is no reference anymore to the freely falling frame, and that is kind of neat. And so that is achieved by this Relativity connection gamma lambda mu nu. All right, so that's the end of today's lectures. Unless you have any questions or comments, don't be shy. Yes?
Can I ask, in GR theory, the speed of light in the gravitational field is due to constant?
The speed of light in a vacuum where you have flat space is constant, yes. But the metric, right, enters into the relationship between the proper time interval and the time interval. And so as a result, there are variations over space. Yeah. So it is no longer, cannot be considered constant anymore, right? Any other questions?
But Einstein's insight, which is that special relativity implies that we can curve space, makes me think that the speed of the something's moving depends on, curvature depends on the speed. That's not really true.
Of course. Well, no, there's another, you're talking about the speed, perhaps the speed of an object that is moving, right? That would be the velocity, right? You're talking about something that is dx mu by d tom, right? That would be the velocity, the forward velocity of a particle, right? The speed of light is something else, right?
But if you're relativistic, you're moving relativistically. That's what gave him the insight about curved space.
Yes.
Right.
Right.
So
And
there
that's
should be some connection.
right.
If
And
there
that
was
c,
no, there should-
right. And that c will depend locally, right? It will depend on you know, it will depend on the local situation, how much of that curvature you have, right? So that curvature has to become at some point part of the formalism, and we are still a long way from that because that's the Riemann tensor, right? So we are working slowly our way to understanding how curved space-time arises out of this formalism. There is no notion of curvature yet, right? But there is a metric. Right? There is a metric, which is an object that, you know, we are familiar already from changing coordinates in spherical, cylindrical, and so forth. So, any other comments or questions? All right, so I'll see you on Thursday then.